Hey, thank you for joining us today for our webinar from the INSITE program. This is the last in our current webinar series. This time focused on marine monitoring. My name is Henk van Rijn, and I am on the INSITE program director team, and I'm going to introduce the webinar today. Before we go into the presentations, though, I wanted to make a point about the use of science in decision-making. Those in government who are making decisions are invariably dealing with multiple and competing interests, and their decisions need to be made in a transparent, accountable, and proportionate way. The science now plays a critical role in informing decision-making and enabling action, particularly in identifying alternatives and clarifying the costs and benefits of particular courses of action so that policymakers can choose between them. And the INSITE program has been looking at some of the fundamental science questions needed to understand the influence and the value of structures in our marine environment over the last 10 years. What we've been doing in the program over the last year, and will continue doing over the next 6 months, is to work closely with policymakers to identify where INSITE science can support their work. Now, INSITE is coming to the end of its second phase now. Many of you will be familiar with the program, but it's worth saying that when INSITE was set up, it was the first real joint industry partnership of its kind in UK marine research. This partnership grew over the second phase, bringing together combined interests of offshore industries with the Natural Environment Research Council and the Centre for Environment, Fisheries and Aquaculture Science in a larger, more ambitious program. Now, INSITE's aim has always been to provide stakeholders with the independent scientific evidence to better understand the influence of man-made structures on the ecosystem of the North Sea. And this slide touches briefly on the breadth of work being undertaken across the science program of INSITE's second phase. I'll just say quickly a little bit about the topics there. They're as broad-ranging as foraging by marine predators, testing the limits of the UK autonomous fleet, understanding fish aggregation and blue carbon benefits, reviewing the efficacy of decommissioning strategies, investigating the connectivity across biodiversity associated with marine structures, as well as developing AI approaches to speed up the analysis, and investigating the effects and implications of subsea plastics incorporated into marine structures. So the focus of the webinar today, as I said, is on the monitoring of our marine environment. When we collect observations of a wide variety of things in the sea to better understand them, to answer questions we have, or to try and address the needs of our marine management policies. And whether our questions are, what is the biodiversity in this area, like what this diver is investigating, or what are the long-term impacts of operating and then decommissioning offshore infrastructure? The monitoring activities must be tailored with the question in mind, and then a suitable array of robust, cost-effective, efficient data collection and then assessment methods that operate at the required spatial scales should then be used to address that original question. So today you're going to hear about a few of the exciting new scientific approaches being explored by our INSITE researchers that could be tailored to meet a wide variety of these questions that one day could form the backbone of future marine monitoring programs. To start us off and to introduce the topic, we're very fortunate to be joined by Vicky Castro-Spokes, who leads DEFRA's flagship science innovation program, the Marine Natural Capital and Ecosystem Assessment Program. And she provided us with some insights around the marine monitoring thinking in the program that we'll consider alongside the research findings from the INSITE projects. We will then hear from three of our INSITE principal investigators. Professor Dan Jones from the National Oceanography Centre, talking about the At-Sea project. Dr. Tom Wilding from the Scottish Association of Marine Science, talking about the NS3D project. And Natalie Hicks from the University of Essex, talking about the FUICOMS project. And finally, I will host a short question and answer session towards the end of the webinar, in which there will be an opportunity to ask our speakers any questions you have about their talks today. You will all be muted through the webinar, but you can ask questions or comment as we go along via the Q&A tab at the bottom of your screens. You can also upvote these questions as we go along using the thumbs up icon, and this will highlight any interest in that particular question. In addition to the webinar being recorded, a live illustration will be carried out alongside all the talks and the Q&A session at the end. We'll give you glimpses of this as we go along, but the final images will be made available via the website. One final note before we hear from our first speaker is that as this is the last webinar in the series, we'll be sending out a feedback form afterwards to gather your thoughts on our webinars, the content and the outputs that we've made available on our website. So I'm going to come back to this just before we finish, so please don't run away early. For now, though, we hope you enjoy the webinar, and I will hand over to our first speaker, Vicky Castro-Spoke, please.
Good
That's you, Vicky.
Good morning, everybody. Can you see that? I hope you can see the slide. My name is Vicky Castro-Spokes, and I lead the Marine Natural Capital and Ecosystem Assessment Programme at DEFRA. And today I'm going to briefly touch upon how the changing policy landscape and the needs for marine monitoring are evolving, and how the Marine Natural Capital and Ecosystem Assessment Programme is at the centre of changing ambitions. So the UK is steward to over 880,000 square kilometres of marine environment by the sea floor area. UK marine and fisheries monitoring is large and complex, and as this slide shows, it covers an extensive breadth of thematic areas ranging from biodiversity through to commercial fish and underwater noise. Here at DEFRA and out across all our partners, monitoring is critical for a number of reasons. Firstly, it's a foundation to assessing the health of our marine environment. It ensures government's reporting and assessments of obligations are met, particularly through the UK Marine Strategy and OSPAR. It will enable us to measure progress against targets such as those outlined in the Environmental Improvement Plan, and it helps us to better understand the effectiveness of the management measures and policy interventions. But we have a really fast and rapidly evolving, changing policy landscape. Since leaving the EU, the marine and fisheries policy landscape has evolved at pace, with the introduction of the Fisheries Act in 2020 and the Environment Act in 2021, both placing this requirement to consider the environment at an ecosystem level. So consequently, the demands for marine and fisheries monitoring data and the insights which these data can generate continue to increase. In order to maximise the impact monitoring can make against a rapidly evolving policy backdrop, there also has to come a change of approach. Our marine monitoring landscape is fragmented. It often focuses on individual policy needs, and data is located in a plethora of areas. So to advance monitoring, we need to better understand how we can manage the marine environment at a systems level. And in particular, there are three elements which I would like to draw out. Firstly, the need to advance monitoring beyond discrete programmes by building a coherent system which begins to increase integrated monitoring through time. This will both support ecosystems and natural capital-based approaches, bringing together data across themes and to help ensure monitoring achieves maximum return on investment by effectively coordinating surveying and data collection efforts. Second, we need to ensure that data collection is standardised using QFAIR and facilitates a collect once, used many times approach. This can be achieved by adhering to data and metadata standards, ensuring that data flows are well documented and that where appropriate, we're using standardised sampling methods. And finally, future monitoring should be effectively leveraging innovation ranging from marine autonomy to measurement approaches to in silico analysis tools. Marine autonomy, for example, has the potential to greatly enhance the coverage of marine data while simultaneously reducing reliance on research vessels and carbon cost of monitoring. Just, can you, I don't know if I've, can you see that? Can you see, I think I've messed up my slides. I'm going to carry on talking.
That's okay, Vicky, carry on.
Is that okay? Yeah, I'm going to carry on talking. It's probably better. So the Marine Natural Capital and Ecosystem Assessment Programme in DEFRA is our £37 million initiative, which aims to advance systems thinking by developing the data, the tools and the approaches necessary to incorporate natural capital policy, natural capital thinking into policy decision making. Monitoring and innovation are central pillars of the programme, and for us this includes enhancing our data collection to be able to fill the key data gaps in our understanding of natural capital and ecosystem assessment, whilst developing monitoring plans for sustained natural capital and data collection. Investment in innovation. With Innovate UK, we've really excitedly had this 2-year partnership developing a novel end-to-end biodiversity monitoring solutions and investing in innovation at higher technology readiness levels with market-ready innovation, whilst also trialling novel techniques through our monitoring work streams. And finally, we're also developing a digital solution where we're focusing on bringing together natural capital and ecosystem assessment data into a single catalogue, making it readily findable for users both marine and terrestrial environments. So before I pass back to Henk, I'd like to close by just thanking colleagues today for inviting me to the INSITE workshop and reiterating the importance of systems level monitoring and data collection in the marine environment so that we can ensure and protect the wide range of the marine environment's needs are met.
Thank you, Vicky. You've really covered a huge amount of work that you've got on at the minute, and that the government's looking at. So I think it's really good, and it sort of shows us that there's massive context for this work. So really great to get that outline. Thank you very much. And with that, now we'll move on to the first of our INSITE science speakers. If I can welcome in Professor Dan Jones, who's going to talk to us a little bit about his work in the at-sea project.
Great, thanks very much, Henk, and thanks everyone for being here and the invitation to speak. So as Henk says, hopefully you can see my slides. I'm going to be talking about our project at sea, which is very much trying to use the latest in marine autonomous technologies to try and address this question around what can we monitor in the marine environment. And this is the work of a large group of people, including science side, but also including our AUV team at the National Oceanography Centre where we're based. Right, so as a bit of background, we probably all know that the North Sea is a very busy place. It's an area with a lot of oil and gas installations, large numbers of pipelines, and many of these are already into the decommissioning phase, and most will need to be decommissioned by 2050. So this presents a massive monitoring challenge. There's also several options for decommissioning, each of which have their own specific environmental challenges and potentially interests around them. It's also an area with lots of other things going on. There's loads of fishing activity, busy shipping lanes. So it's an area that's got monitoring challenges, but it's also an area that's difficult to monitor. The challenges really relate to the structures themselves that have been installed, mostly through oil and gas, but increasingly through offshore energy. And these structures have positive and negative effects. And these decisions around how to decommission them need to be made in collaboration between the companies and their regulator, but they all require robust scientific evidence which can be gathered through environmental survey and monitoring. Of course, this all requires a large amount of survey activity to be done, both in terms of in space, looking at all of these different installations, but also in time as they require repeat monitoring. And this project at sea is very much investigating whether there can be an evolution in the way that we carry out this marine autonomous, we carry out environmental survey using marine autonomy. And we're trying to investigate through doing a trial mission if we can meet these challenges and transform the way that we do environmental monitoring. We believe that there can be a reduced cost or conversely a greater mission frequency for the same cost. We can do the work with smaller teams. We can increase safety and all of that with a lower carbon footprint. But the key question remains, can autonomous systems provide the environmental evidence needed, and can they actually get to the places where we need to collect the evidence? So the aim of the project is to demonstrate the feasibility and value of this autonomous monitoring. So we wanted to carry out the monitoring itself, do a trial run without a support vessel, so launching an AUV from shore to carry out environmental monitoring in the North Sea. We wanted to integrate different data sets collected by the autonomous platform. We wanted to compare those data with that obtained using standard approaches. And we wanted to demonstrate if that fully autonomous approach can really lead to the advances that we would like to see. We successfully carried out 2 missions at the end of last year. And the first mission was to Northwest Hutton, and the second was to the Braemar Pot Marks and the Miller Field, so 2 decommissioning fields. Both missions were carried out from shore at Lerwick in Shetland. Total, the 2 missions took just over 20 days. They covered 1,000 kilometers, and they used 21 kilowatt hours of energy, which is the equivalent energy in 2 liters of diesel, to give you a feel. So this is a very efficient method for doing the environmental assessment. During those surveys, we collected 86 hectares of microbathymetry, millions of photographs, including nearly 80,000 colour photos. And as well as that, we collected a whole lot of additional sensor-based data. So acoustic Doppler current profiler, CTD data, hydrocarbon sensor data throughout these missions. We didn't have an eDNA sensor, but we have in the past fitted an eDNA sensor to this vehicle. We couldn't on this one because of the battery, but that's an area that could be improved into the future. So we were looking at trying to meet some of the key environmental monitoring targets, and I just thought I'd put some of those up to set the scene for the rest of the presentation. And really, we're trying to understand the role of structures in the environment. We need to understand how the atmosphere, water column, and seafloor interact, and what the challenges are for the environment in those. We need to look at the structures themselves, including things like pipelines and also cuttings piles around the structures. And in each of those areas, we need to look at chemical impacts, physical, biological impacts, and then there's other related challenges around it, around understanding what hazards are there and the sort of debris that's left after a decommissioning operation. So I'm going to give a feel for the data that we collected using the autonomous system and show how it can answer sort of key questions, but also how it compares with data that were collected either as part of this project or as part of other projects using standard shipborne operations. So I'm going to start with looking at the physical seafloor environment. And mostly the assessment of this, at least at the broader scale, is done through acoustic mapping. And the acoustic mapping can be carried, like for example, with multi-beam, can be carried out pretty much independently of the platform. So you can do this with an autonomous system. You can also do it with a ship. And if you're mapping near the surface, you get similar results with a similar sort of pieces of equipment. With the AUV, you have the option of going closer to the seafloor and getting much higher resolution imagery. It's also possible, because of the reduced costs of surveys, to carry out these surveys multiple times and look at changes in the physical environment, which is quite important when you're trying to understand the evolving seafloor environment around a decommissioning program. The AUV can also collect seafloor imagery, as can a ship, but the AUV can do it in a very rapid way, but it couldn't go near the structure. So we were able to collect 1 centimetre resolution bathymetry data, actually a bit higher than that, in quite a large area around the Northwest Hutton platform, as the example with the blue background there. We were also able to collect simultaneously these high resolution seafloor photographs, and you can see an example of the zoomed in microbathymetry, where you're looking at sub-centimetre scale changes in the height of the seafloor around this hexagonal structure, and then you are looking at the photograph underneath it. What we can't do with autonomous systems is looking at the sediments themselves. We can't sample the sediments, and we can't look at grain size, for example, but then we might be able to get some proxies in imagery. We were able to collect data on the physical water column, answering the question of what the role of the structure in terms of changing the current flow direction, and also looking at particulates in the water. Again, we couldn't sample the water. We looked at chemical impacts based on sensors, and this plot in the middle shows the sensor looking at methane over the Braemar pot marks. The Braemar pot marks are a marine protected area, but they're also an area where we know there's natural leakage of methane through pot marks. And we were able to detect this fairly clearly in the sensor-based data on the AUV. And we can cover quite a wide area quickly, but there are still some sensor issues, like it takes a long time for the sensors to stabilize. Big peaks are obvious, but I think the detection limits are relatively limited. We also looked at evidence of oil in water. We didn't find any in the data, we didn't expect to. But with standard shipboard sampling, you can get high detection limits. You can sample sediments and water, although they're slower and more expensive. The biological environment, it was quite a focus for us. And we found that the two different approaches focus on a very different scale. The AUV can do very rapid assessment over a large area, but it can only assess at the moment the larger fauna. This problem is fixable effectively. The AUV can go closer to the seafloor, and it can get more information on the smaller size classes of animals, which are really the ones of relevance. The AUV operations were also very important in putting the faunal observations in context, so you can get a much better feel for the different habitats present in the area. You can look at the difference between the cuttings, mud, gravel, and you can see that these have different faunal assemblages associated with them, and also no doubt have different monitoring challenges. But it needs support from standard approaches. We can't do one of the key approaches, which Natalie is going to be talking about later, around looking at the animals living within the sediments themselves. So it's a big gap as well. We were able, using autonomous methods, to address other aspects as well, as sort of value-added things, looking at debris on the seafloor, looking at the litter, and also place structures, looking, example, of pipeline state and condition, and looking at impacts on the seafloor. We could see, for example, quite a large area of the seafloor was impacted by cuttings, which we were able to delineate based on the AUV data. So there's lots of value-added approaches there. So I thought it'd be interesting to explore how those AUV data sets meet the recommended monitoring requirements from the decommissioning guidance notes for environmental survey. And we can do quite a large amount of it. We can look pre-decommissioning, looking at cuttings, piles, works. We can get close to them. We can't get close to the structures using this kind of autonomous system. And I know Tom's going to talk in more detail about how you can get some great data on the structures themselves. Once the structure's removed, we can carry out debris surveys. We can verify clearance within the locations and carry out quite a bit of the seafloor environmental survey, although not all of it. And then if the structure's left in place, some of those ongoing survey operations can also be done. In any case, these surveys need to be developed on a site-by-site basis with the regulator. So there's probably room for some discussion about how you can use autonomous systems and what autonomous data can be used in a way to really understand the environment better. So in conclusion, we demonstrated effective remote sensing approaches for a wide range of parameters. We demonstrated that you can do these really quite amazing missions from shore out thousands of kilometers around multiple oil and gas infrastructure at very low cost and emissions and a low risk to personnel. We can't do some of the survey operations, but we can do a good percentage of them. And I think there's a lot of work ongoing to see whether we can use these remote sense data as a proxy for some of the missed information. There's lots of opportunities for extending this approach beyond decommissioning, looking at marine protected area monitoring, blue carbon, natural capital. So there's lots of potential. And I think really what we're seeing at the moment, I think what we'd recommend is that these autonomous systems can be used very effectively in a complementary approach. You can combine the best bits of autonomous survey to really understand the environment, to carry out the broad scale assessment, to allow much more refined targeted sampling with the ship saving time and money. So with that, I'll say thank you very much, and that's the end of my presentation.
Thank you, Dan. Some really interesting stuff you shared there. I think even from the cold water corals on the decommissioned structure, I mean, that's quite impressive to see, but also really sort of getting into the range of capabilities that we see with AUV technology. And I think one of the things that really rings a chord with me anyway is that you can put a wide range of sampling devices on the platforms, and then because it's the one platform, you can look at the relationships between those different data types. And so depending on what you collect, that could be incredibly useful for more sort of ecosystem wide approaches that there are increasing needs for. So thanks for sharing that. You've already got a couple of questions, which is great, but we'll get to that at the end. For now, though, thank you again, and we'll move on to our next speaker. So can we hear now from Dr. Tom Wilding, please, who is going to talk to us a little bit about the North Sea 3D project. Over to you, Tom.
Thank you, Hank. Could you just confirm you can hear me and see the screen? Yes. Okay, great.
All good, Tom. Thanks.
Thank you. Thanks very much. Okay, so I'm Tom Wilding, and I'm a benthic ecologist. I work at SAMS, the Scottish Association for Marine Science. I'm going to be talking about some of the work that we're doing under INSITE Phase 2, which is around machine-assisted image analysis and in relation to monitoring of structures. And I'm extending that to the seabed for the purposes of this presentation. So what I'll be talking about is giving a little bit of background to the context in relation to monitoring using image analysis. So scales are particularly pertinent to that. Then go on to talk about some of the challenges and opportunities associated with machine-assisted image analysis, with a brief whiz through some 3D and the 4D photogrammetry work that we are doing as part of the INSITE program, with a sort of vision and a wrap-up at the end. So in relation to monitoring scales, as Hank said in the introduction there, these need to link to the objectives, and on the XY coordinates there of spatial and temporal scale, we could look at man-made structures operating at a relatively smaller scale of 1 to 10 kilometers over several years, whereas arrays of devices like offshore wind farms are going to be operating at hundreds of kilometers squared for periods of 25 years. Whereas the ecosystem services, which we all rely on and which are an important part of the regulation and the policy, as Vicky alluded to at the top there, at larger scales. Now, this axis of time and space is of increasing policy relevance, and that is increasing over time as we adjust to looking at ecosystem level delivery. But these, as Dan has alluded to, really are associated with increased monitoring and assessment costs. So how can image analysis fit into that? And that's the subject of the INSITE Phase 3 project, North Sea 3D, which I'm leading. So what we are doing is we are taking industry data, and it's worth noting here that the technology is delivering ever more data, and this is becoming cheaper and cheaper as underwater camera systems like remotely operated vehicles get cheaper to buy. And as Dan has alluded to, autonomous image collection is already here, and that's only likely to increase as robotics becomes more and more mainstream within the marine environment. And there are thousands or tens of thousands of hours of seabed video in various archives within the sector. However, the analysis of video footage is very time consuming, And because it's time consuming, it's very expensive. And a big disadvantage of human-based analysis is that the resultant data is very inconsistent. Humans vary in their interpretation of the same video footage depending on what side of the day it is and what end of the week it is. Machines, though, are better or don't have that disadvantage. Of course, they work 24/7 and they only get better with increasing training. They don't tire during the day or during the week. They don't retire and move on, which is another major advantage. And they are consistent in the outputs they produce. Now, underwater images come with a number of challenges. Underwater footage varies considerably between operators, depending on the hardware they're using, whether it's an ROV or an AUV or some other camera system. The deployment protocols that are being employed for any particular task and the standard operating procedures accompanying them will vary. And a key issue there is the distance to the subject in ROV footage or the altitude that the AUV is flying at. And there are many more sources of variation in relation to underwater footage, which the machine needs to be trained around. There are also issues of color attenuation, with red light being preferentially absorbed by seawater, meaning that normally artificial lighting is required for most surveys. But that brings its own challenges of introducing what can be quite large shadows into the imagery, which again, the machine needs to be trained about or around. And there, of course, is issues of water turbidity, particularly when the imaging device touches the seabed. And there's motion blur and many more things beside. Excuse me. However, despite these challenges, the initial results of our data analysis are very encouraging. And what I'm going to show now is just an example of a YOLO model. That's a you only look once model being applied to a sponge bed off Greenland. This is footage that we gathered, so we can freely use it. And this model is just going to draw or draws boxes around the three target taxa that it's been trained on, and those taxa are urchins and two types of sponge. So hopefully we'll look at that. This is the freeze grab from the start of the footage. You can run this in real time, but this has been applied post hoc. And as you go along, the machine just identifies the key taxa that it's been trained on, even though the footage is quite ropey and with big shadows and the sledge impacting the seabed occasionally, as you can see from that. It's slightly jerky footage because we've subsampled this to make it more manageable. Once the footage has been obtained, we can extract the data. If the video has got is geo-referenced, we can extract coordinates and basically just map out the data in much the same way as we would with any other technique. But with image analysis being employed, we can do that. We can realistically and cost effectively map out a great deal more data and interpret it interpolate between the data points and interpret it in the same way as usual. We can also combine 3D photogrammetry with auto identification. So just what is 3D photogrammetry then? Well, it's the science of generating 3D models from multiple images and extracting information from those models. And that information can include the volume of the organisms being visualized, and via a calibration curve, we can estimate the biomass of those organisms. And this reveals something which is really interesting from an ecological perspective, because the models enable assessment beyond counting. So there are metrics of health that you can determine from these 3D models, in addition to the volume and the biomass. So in terms of deriving the biomass, what we do is we generate a 3D model, and that's shown there. That's a 3D model of a rocky seabed that we developed. We then apply the auto ID. In this case, there's three key taxa of interest there. The red blobs being urchins and the green being Metridium dianthus, the anemone. And we can then isolate particular taxa, remove the underlying rock, and derive the volume of those organisms from that type of model. And I'll show you, and I'll show you another. I'll show you. Excuse me. No. I'll show you another model in a moment. Are we all right to continue? I had a Teams call.
Oh, yes, carry on.
Yeah,
carry
sorry.
on, John. Yep.
I'm just no. Yeah, sorry about that. And so we had we can make volume predictions, and I'll show you this in a moment. So this is just a 3D model. It's actually taken from an aquarium of a concrete block, as you can see, and it shows you the development of the model and how an individual taxa a change in their volume, and we can measure that using our technique. And that's the calibration curve, which I won't touch on now. So this next animation shows you an ROV image of the type that we normally collect or obtain from our industry partners. That's under the white bar, and then the model generated from it with the auto ID placed on top. So you can see, I hope, the ROV footage, and then that's the 3D model, and then on top of that, we're now superimposing the auto ID. We've got CAD figures for those sorts of structural elements, and we can extract the underlying structure from the overall model volume to leave the volume of the marine growth that's growing on there. We can extend this to 4D analysis using a multi-camera setup. This is at the early stages of development at SAMS at the moment. So this is basically 3D photogrammetry over time. And this enables the measurements of behavior and size change of organisms over time, and as you apply different treatments to them. And the one that we're most interested in is the response they make to being fed, basically. And we can look at any point at any time here. So this is a tank set up at this stage. It's a bit of a rough and ready model. Again, this is early days. This is taken using 8 time-synced GoPro cameras around these particular subjects, and we can play this and just show you the urchins moving around, annoyingly out of shot of the camera as far as the urchin. This is sped up, of course, but we can stop that model at any point and spin it around and look at any part of those organisms as they respond to treatments. It's a fascinating approach. Machine assisted image analysis. We've trained multiple taxa across multiple taxa so far, so that includes marine growth on structures and other organisms on the seabed. And the machines are really excellent where the training is sufficiently extensive, i.e., we've applied this to coralline algae on Merle and other priority marine features. And we're currently working on multispectral data and data fusion by incorporating acoustic data into the machine training process. To conclude then, innovations in data collection technology mean that we're getting more high quality data, and it's covering more ground, and it's cheaper, and this is allowing more appropriately scaled and high resolution monitoring, which is a great thing. But we need machines to help in the interpretation and analysis of that massive data that's going to be coming in, and this will only increase. I think this will assist us in determining trajectories of things like marine net gain or habitat restoration or other policy goals. I'll conclude there. Thanks to the team, some of whom are shown above there, and my sponsors, including INSITE, of course, and I'll take questions at the end. Hank, thank you very much indeed, and thank you everyone for your attention.
Yes, thank you, Tom. I think you've shown us some, pretty marvelous stuff there. It's really, really great that that your animations worked as well. It really, really illustrates the potential of a lot of this technology, and I can see linkages with what Dan showed us earlier on as well. You also make good point around making better use of the machines, and that yes, machines don't need to sleep and they don't need to retire. Like, I really like that point too. So I think with all those in mind, we're going to keep building things and move on our next speaker. So thanks again, Tom. And just before we go on to our next speaker, I've noticed quite a few questions appearing in the question tab. That's brilliant. Can you think about upvoting any of those if you really like them? And equally so, if you've got any new questions for Tom, Dan, or Vicky, or any for Natalie, feel free to pop them in as well, and we'll try to get through as many of those as we can after that. So without any further ado, hand over to Natalie, please.
Thanks,
Dr.
Hank.
Natalie Hicks. Yeah.
Brilliant, thank you. Okay, pleased to be the last speaker. I will be taking us out of the autonomous and into the seabed. And I'll be giving an overview of some of our data collected under our INSITE FewComms project. And today we're looking at the data through the scope of marine monitoring. And I'll be presenting some data that we've collected recently and finished analyzing, and looking at the legacy of decommissioned oil and gas platforms and what this means for marine monitoring. So Dan touched on this in his talk, that traditional monitoring approaches to assessing impact of a structure or pollution or anything really often includes a large biodiversity element. And there's an increasing interest in understanding and measuring our biodiversity, whether it's as an impact or for marine net gain. And the traditional way of doing this, by collecting sediment and sieving it, and then using skilled taxonomists to explore the biodiversity of the macrofauna, is particularly time consuming. It can be quite expensive, and there's specific skill sets required, plus the logistics around collecting these samples, which are often large amounts of sediment. This is where eDNA provides a potential to improve our ability to monitor biodiversity, but provides us an opportunity to understand the environment a little bit more widely. In order to use eDNA, you do really need to understand what you're measuring, and there's different approaches to measuring eDNA based on what you want to know or what you're asking. And Hank talked about this initially. You need to really understand what you're trying to measure and why. And there's also a number of limitations to the approaching eDNA. And when we talk about eDNA in our project, although we're looking at merging eDNA approaches to measure macrofauna, what we do focus a lot on is understanding the microbial eDNA. Microbes are really what drives a lot of our systems, particularly in the seabed, and they're really important for nutrient cycling, so driving a lot of the biogeochemistry. They're a really great indicator for the general health of the seabed based on what microbes might be there or might not be there, so what's present and what's absent. But they also allude to some of the pollutants, such as hydrocarbons or metals, that we might find in the sediment. So understanding the microbial eDNA is really key for giving us a sort of snapshot of the health of the seabed. So the data I'll present today have been collected around 2 decommissioned sites, which are quite nicely the 2 that Dan mentioned in his talk. So we've got Northwest Hutton to the far north, just between Shetland and Norway. And we've got Miller Platform a little further south. They've both been decommissioned, although the legs have been left within the seabed and remain there now, but the top of the platform has gone. Northwest Hutton was finished decommissioning in 2009, and Miller was decommissioned in 2018. So we've got a slight difference in the time since decommissioning. And we really wanted to understand whether there is a legacy impact. Can we measure the impact of the platform perhaps during its production phase in the seabed now, and how long does that last for? So we collected sediment samples at an increasing gradient around each one of these sites, 2 gradients per site, starting at 50 meters in proximity to the platform, and then doubling our distance as we moved away, with our control site set as 3.2 kilometers away from each side along the gradient. And we measured a number of different things. I'm not presenting all of that data here today, but what I will present is some of our biodiversity data for the macrofauna and the microbial communities, and a little bit of the chemistry and the metals data. So this is a really colorful plot. These are our traditional biodiversity measures. So this is the macrofauna. So this is sediment that was collected in the traditional way and served. And then one of our collaborators at St Andrews spent a significant amount of her time picking through each sample and identifying them. So we've got Miller on the left-hand side here and Northwest Hutton on the right-hand side. And the different colors represent the different genera within that. Along the bottom, we've got our distance gradient starting from 50 meters and increasing with distance as we move away for each of the platforms. And the amount of space that each color takes up indicates the relative abundance of each genus. You will will note that we don't have a control site for Miller, although this is still a relatively low impacted or non-impacted zone. And this is partly due to the logistics of collecting sediment on some of the cruisers due to weather. And since we need quite a lot of sediment for a standardized macrofauna biodiversity analysis, we don't have one for Miller. But what you can see, if you look at both of them in terms of the color, you can see that the columns closest to the platform, so the 50 meter, for each of them has a slightly different diversity or community structure compared to the rest of the structure as we move away from the platform. So for example, you can see at Miller, we've got a huge dominance of echinocardium as we move further away. And we see different community structure at Northwest Hutton, but particularly different makeup of that community at 50 meters. And as we move further away, we start to see the seabed return to what a baseline or control might look like, and the community assemblages look more similar to what we'd expect. A lot of what's determining this, as well as the presence of the decommissioned site, is the sediment type. So we know that Miller is a lot sandier than Northwest Hutton, which is much muddier, and that will have an impact on the biodiversity. In terms of how this looks from an eDNA perspective, so this is the microbial biodiversity, and we've got, again, the same two sites, so Miller on the left-hand side and Northwest Hutton on the right. And again, the colors represent the different genera that we measured. And so this is just different microbial communities. And you can see, again, we start to have differences at the 50 meter, perhaps not so much in what is found there, but we are seeing differences in the relative abundance. And because we only need a small amount of sediment for the eDNA analysis, we have got data for the Miller site. So it's a lot easier to collect a small amount of data than it is to collect quite a large amount. I'm going to go into a little bit more detail, focusing on the Northwest Hutton now. But what you can see across them are different changes in the amount of, say, the yellow, if I highlight the yellow bars here, and the blue bars at the top. And we can see an increase in the amount of red at the bottom here. And this is down to some of the different species changing in abundance in close proximity to the site and as we move away. So we can see the blues and the yellows, which we can see are in higher relative abundance closer to the platform, we know are really important for sulfur cycling. So we've got the sulphuravorum, which are sulfur oxidizing bacteria, and they remove hydrogen sulfide, whereas the desulfatic glands, I'm sure I probably not pronounced that properly, are the sulfate reducing bacteria. So these are a little bit of a feedback loop. And generally where we have a large amount of sulfur cycling microbes, that's an indication that the sediment may not be healthy or very oxic. And so it's suggesting that they're still quite impacted. And then we are seeing an increase in the sort of red color as we move away into our control zone, and that back to what we've considered background levels. And this genus is a biomarker of what we would term healthy marine sediments. And so often where you have high hydrocarbons, you tend to find not very many of them. And so you can see the relative abundance increases as we move away. And we know from our own hydrocarbon analysis that our hydrocarbons also declines at the same time. And just to prove that, the biology is very closely linked to the chemistry. We have a number of chemical analyses as well, and these are some of them. So we talked about the role of the sulfur bacteria, and you can see that particularly very close to the structure here, that we've got a huge amount increase in the variability of sulfate that we find in the surface sediments. We also see changes in the pH, particularly close to the platform. And we've also got increases in hydrocarbons. So these are total alkanes and total PAHs. And you can see, and we saw the same trend again at Miller, that despite the platform having been decommissioned over a decade ago when the samples were collected, we're still seeing high levels of hydrocarbons, quite close proximity to the platform. And then just as a sort of snapshot, we know that the metals play a role as well. And we know they play a role in terms of microbial communities. And so we've measured some of the metals. And what we've got here, we've got chromium with the two platforms, measures for two platforms, copper, Miller on the left, Northwest Hutton on the right. And again, we've got zinc and lead. And with the exception of lead at Miller platform, all of them are very high, very close to the platform. So this is irrespective of the decommissioning time since the platforms were decommissioned. And the dotted lines just represent sort of values, so ballpark values. So we know the US EPA use different values as an indication of medium pollution or heavy pollution, and that's what these bars represent here. We, in the process of disentangling the relationship between the concentration of metals and how the microbial communities respond to them using different eDNA approaches. Our student Haley is actually in the middle of running a huge mesocosm experiment at the moment, looking at the independent and multi-stressor impacts of some of the metals. So this is some work in the pipeline still to come. So in terms of our key messages, we can see clearly, irrespective of what measure we're using, there is a legacy of impact on the seabed from the decommissioned platform sites, whether we're measuring this in biodiversity or whether we're looking at the chemistry or metals. However, eDNA has a real potential to play a big part in our future marine monitoring, and this could be feeding into marine net gain of existing structures, and it's something that renewables are particularly interested in, but also gives us a little bit of an insight into the seabed itself. So it's not just telling us what the biodiversity of the microbial communities are, it's telling us what is happening in the chemistry and other associated factors within the seabed too. So it's almost like a biomarker. In using eDNA itself, we can be very general. So we could say, what is the biodiversity or what is the abundance, like what I presented today? Or we could be a little bit more targeted in our eDNA approach and go, okay, so we know roughly who's there, but what are they doing? So using metagenomics approaches allows us to target specific functional traits or functional genes. And this could be things like hydrocarbon microbial bacteria, microbes that are really important for nitrogen cycling, depending on what the target might be. And as Dan said in his presentation, you'd very much want to tailor it to each site or perhaps what you're looking to measure. So understanding not only the diversity in terms of who's there and how abundant they are, but what they're actually doing within the seabed itself. And this opens up a whole range of questions. What is the relative impact on existing structures such as renewables? And we're doing some work on that at the moment, so that'll be coming out in the next year or so. What we don't really understand is the temporal variability. How long is it before we may see a decommissioned site go back to baseline levels? And again, this is likely to change on a site-by-site basis. And what are the implications and the role of marine monitoring if we decided to take different decommissioning options? So instead of fully decommissioning, maybe we need partial decommissioning. What sort of marine monitoring programs would we have there? And what would the role of things like eDNA play in this? So with that, I'm going to conclude for now. Very happy to take any questions, and a huge thanks to the extensive team outside of just Essex who have been really instrumental in bringing this together. Over to you, Hank.
Thank you, Natalie. Thank you. You raised in the final minutes you talk there some really interesting questions for us all to consider about the applicability of these exciting technologies and approaches, and but the applicability of those to kind of future policy needs, as well as the current policy needs. I know there's a lot of discussion at the minute over decommissioning approaches, and yes, I think there's some interesting questions there around which techniques could be useful for that. And then yes, I did not know myself that you could get a relative abundance measures from using eDNA samples as well, which is really great. That shows that how much the technology has moved on in even just a few years. So thank you for sharing all of those insights, and again to all of our speakers there who've really brilliantly covered a lot of ground and a lot of different techniques and technologies there. And our audience have started to fill in some questions for us to answer. So if I can welcome our speakers all back on, we're going to have a panel discussion for about half an hour now or so. Just as we're getting started, we can have a little glimpse at the illustration that's being drawn live while we've all been talking and listening, and you can see there it's starting to take shape. Got some great sort of infographics rocking up there. Thank you very much for showing that. Okay, in terms of our questions, I think picking up on something that Natalie has just said there, I'd like to carry on with that a little bit. There's a question that we've got from one of our attendees, and I think it might be interesting to start with Natalie and then maybe move on to Vicky a little bit with this. And it's around what monitoring, if you know about what monitoring currently exists around decommissioned structures, and from that, are there environmental impacts that are being observed around the structures that you're aware of, noise, benthic disturbance, and so on? I can ask Natalie that, please.
Sure. I wouldn't know a huge amount about noise, although obviously some of our other INSITE projects have been looking at various aspects of that too, which may touch on that sort of acoustics aspect. In terms of monitoring, I believe oil and gas companies do have an obligation to monitor, but how regularly or how in depth that is. And I can see someone's asked about microbial eDNA. That is most definitely not part of it. And we're almost missing a trick there, because if you're doing eDNA anyway, why you're not focusing on the microbial communities, that would actually tell you a lot more about the health of the status. So yeah, and shall I answer another question while I can see it?
Oh, of course. Which question would you like, Natalie?
So I can see Sam's are asked about the eDNA from sediment samples. We did not extract from water samples at this site. We weren't actually on the cruise for this. Someone else very kindly collected the samples, but we have collected from the next sampling campaign that we just completed. eDNA and water will probably be a lot more dilute. Sediment is full of microbes, so it's a great place to do microbial analysis. And also, since water is so mobile, it's unlikely that you would pick up the same level of signal, so you get a sort of concentration within the sediment. So that's why we do sediments. But of course, it is good to know what the eDNA is in the water column, and if you've got sort of baseline communities that you can subtract from your own values.
Yeah. Okay. Thank you, Natalie. Just to round off the previous question around the environmental monitoring around decommissioned structures, is there anything that you know about that, Vicky?
No. So to be honest, I'm not aware of anything that's in train, but I do think for once we have an opportunity to be on the front foot, and I think it's something that we need to start looking into in the near term, because as well, I think the question would also be around, is it right? What is the impact of moving even the structures? What's a new ecosystem that's been created around these structures, and what would be the impact by their removal? So I think this is something that we need to pick up at the centre and start to work through options on. Yes.
Thank you, Vicky. A question then for if we go to Dan. So Dan, I think you might have answered this in the chat, but it'd be quite good to open that up to the audience as well. And it's just wondering around whether there are issues around exclusion or safety zones around offshore installations, and yeah, what are the challenges with flying a pre-programmed expensive machine in and around these structures?
Yeah, so it's a very good question, and I think this is one of the big areas we spent a lot of time and effort in terms of planning the autonomous deployments that we actually did. We have a marine autonomous vehicle team that are sort of up to date on all the regulations, but to my knowledge, and bear in mind I'm a biologist here and not a legal expert, there is the AUV operations are quite a grey area in terms of what you're allowed to do and what you're not allowed to do. And we were using a subsurface vehicle, and there's also differences, I think, between surface vehicles, so AUVs operating at the surface all the time and AUVs operating at the surface briefly. So we were typically at the surface 2 or 3 times a day during the deployment. So we came to the surface to get navigational fix because we don't get perfect positioning underwater. We use relative positioning. So there's lots of issues around that. We had to spend a lot of time developing our risk assessment, hazard assessment, and we used a variety of tools for that. We also put out notices to mariners to try and notify people that there would be a strange yellow submarine flying around the North Sea. We were concerned it would get fished or blown up by the MOD, worried what it was. So we tried very hard to make sure that the various ocean users were aware of the operations. With regards to exclusion zones, the sites we went to were decommissioned, so the exclusion zone had been removed. There was no ongoing operations at that site. There was still structures on the seafloor, but they were cut off, so they were well out of navigational safety concerns. So we were able to go to those sites, but we had a lot of discussions with the operators of those sites, or the sort of the owners, to make sure that they were happy and were aware of what we were doing, and that they were not planning any operations going on at the same time. We also had to discuss around people that owned pipelines that we were going close to, and put in place proximity agreements to go near those. So it is quite complicated. Part of the role of part of the outputs of the at-sea project will be a very detailed document about how we carried out the mission, so other people can learn from how we did it, and we can pass on the sort of all of the lessons that we encountered and different outputs from the various discussions we had with stakeholders. So yeah, it's a challenging area, but you also have to remember that this vehicle, although it's quite big, it's about 3 meters long, it's neutrally buoyant, it's so it weighs nothing in water, it's traveling at a slow walking pace. Really, the damage it can do to other things is relatively limited. It's more likely to be damaged itself. And I think our biggest concern on that front was entangling in old fishing nets or debris on the seafloor, or the structures themselves. Our navigational accuracy was quite good, but not perfect. And there's a lot of uncertainties in these areas that have received extensive use since the 1970s.
Yeah. It does sound quite intricate in terms of the planning there, and I think sharing a little bit of kind of lessons learned, of the process that you've been through will be very helpful for future researchers following in this path too. So thinking then about the structures and moving on to more ROVs that are used along the structures and the footage that's collected there. Tom, I know this is what you've used quite a bit in your research, and we've got a question around what sort of representation you think you've got so far from the ROV footage that you've been able to get access to and use, that's been of the right quality, and then that you've been able to make the models that you showed us earlier on. What sort of representation have you got so far, you think, of general biodiversity around these structures? Is it sufficient in your opinion, or would more need to be done?
Well, there are clearly thousands of structures in the North Sea. We've had access to several of those. Ideally, as a data scientist, I always want more data. So, and that would apply here as well. Ideally, I would like more structures. We've really proven the technology in a sense, converting ROV footage that's gathered by industry. We can convert that to models from which we can extract bio volume and from that biomass. And we would like more footage from other structures, and we're still open to data provision by anyone. That in a sense, this could be a call out for that to highlight that again. That whilst we have a good coverage, particularly in certain locations within the North Sea, we would like more data.
Yes, it's quite a good opportunity to make that call again, Tom, I think. And for anyone on the call today, I think you've seen the kind of things that are possible with the right tools and the technologies there. Yes, it'd be good to shunt some of that in Tom's direction if possible. I've got a question around the biomass elements that you were talking about, Tom, and that you can extract from the analysis that you've done. And it's for Vicky, actually, and about I know you're working quite a lot with the natural capital approaches and sort of trying to explore those. And from a monitoring context, I remember from a past life that the biomass was often quite a tricky thing to get if you wanted to get that from structures. I wonder, you know, do you think that that these approaches that Tom's looking at, you know, if you see how you see those fitting in within a natural capital context, you know, if you have information like biomass of reef structures and so on?
So I would have to take that question away, to be honest. I think it's probably just a bit too technical for my pay grade, and I would have to draw on the experts in our team to be able to give that kind of information. But I can surely update you all on views from the team.
Sure thing, Vicky. Yes. Okay, Grant. You know, and I think I think Tom. I think Tom would be interested in that conversation too, and
yeah, he would.
And then and then if we can pivot that also, because we've also seen what some of the eDNA approaches can achieve too, and we've got another question which I direct to Natalie, and it's asking. It's interesting actually, asking about eDNA and whether or not, Natalie, you know, if it's being incorporated into environmental impact assessment surveys. And I know you work beyond the oil and gas platforms, also with increasingly offshore wind research too. Do you know if any of these eDNA approaches are being used in EIA surveys?
No, often the microbes are the forgotten parts of the biodiversity, partly because not that many people understand them, myself included, but I work with amazing colleagues and collaborators who have a really good handle. And it feels like an easy win to include something like that, because it's not only telling you a bit about the biodiversity, but it's telling you about some of the functions as well. So who's doing what? Some colleagues for example, do work on oil spills, and microbes are the ones that break down the hydrocarbons, and looking at the change in communities over time is really useful for indicating who the key players are. So no, it's not part of a standard environmental impact assessment, but I would love to see it becoming increasingly common.
Yeah, great. I think that could be another one.
I should actually link to Tom here as well, because me and Tom work together as well on some of these, and Tom does some great eDNA work around fish farms, and I suspect that's what he's going to jump in with now.
Yes, please, Tom. Let's hear more about that.
Yeah, thanks. So I also lead a project called METBAR, and we're developing bacterial metabarcoding, hence the name, to predict benthic IQI. That's the informal quality index. So we're basically extracting. Well, we're taking grab samples, taking a small subsample for bacterial metabarcoding, putting the rest of the grab through the traditional process, extracting the macroinvertebrates, deriving the informal quality index just as normal, and then training a machine to link the bacterial pattern to the IQI, with a view to removing the requirement to actually determine the IQI using the traditional method. So this sort of bacterial-based IQI is a more cost-effective way of doing it, and it's working extremely well. I would have liked to have included a graphic or two within my presentation on that, but I didn't have time.
Oh,
very happy to.
You only had 10 minutes, Tom. You're able to cover quite a lot in your 10 minutes. But that's a really interesting point about the informal quality index, which currently forms a part of the marine strategy tool set. So I think that could be quite an interesting thing to keep working at, and eventually include that.
Yeah, the IQI is the go-to metric for the Water Framework Directive, and that's the instrument under which, or that's what really governs the regulation of aquaculture in the UK.
Yeah, excellent. Really good to know that. I've got another question, and I think this one we could open up to the panel, and it's an interesting question. There's sort of a two-parter which I'll follow on to in a moment. But it's, first of all, it's looking at the monitoring tools and techniques that that you all work with, and thinking about how and if possible could those be incorporated into future construction of structures, or bolted on to structures in any way. So, for example, an offshore wind turbine could have a pet ROV in the future, or a pet AUV, or oil and gas structures could have them included in with automatic analyzers or eDNA analyzers. So it's a question there really around do we think that's viable? Do we think the technology would work in that way? Would there be issues? Would it be too expensive? Would any of our panel like to muse over that one?
I can have an initial go.
Dan, yes.
So I think the answer is definitely yes. There's a lot of potential for lots of different approaches that will help monitoring in the future, and that ranges from using the power and communication abilities of the infrastructure to support real-time sensor networks. That's actually probably a relatively straightforward, fairly cheap approach, and I think to a certain extent that's used already for some aspects of the environment that have more, say, engineering interests. So yes, definitely on that front. I won't answer on eDNA. I'll leave that to the others. But in terms of having an infrastructure that facilitates monitoring using subsea robotics, then definitely you could have that. You can have, well, some structures already have ROVs associated with them. In terms of autonomous vehicles, having a way to autonomously charge and download data is being considered at the moment. We haven't done extensive trials on that at NOC, but I know other people are doing that, looking at docking systems, for example, or potentially using acoustic modems or whatever to download data as it flies past. But yeah, there's lots of options there. They're probably a little bit further into the future for the autonomous systems, and perhaps very relevant now for the remotely operated systems. But I'll leave others to sort of add their thoughts on that.
Yeah, that's really interesting. I'm sort of thinking of a giant version of wireless mobile phone charging. Natalie.
Yeah, I'll jump in. eDNA, at present, the sort of sequencing aspect of it, where we collect the samples, we send them away, they get sequenced, that comes back, does require specialist equipment, but there are ways of trying to streamline that. So one of our students at the moment is looking at a way of developing effectively a sort of toolkit, lab in a chip sort of thing, which would mean industry partners or non-scientists could take a small sample of sediment and effectively have that analyzed on a little USB in a laptop, and that would tell you pretty much instantly if your target species or traits or genes or whatever are present, so whether there's a presence of hydrocarbons, or has that increased since this time period, or has that gone down, or are we seeing a change? So the technology is moving really quickly, and the aim is to make it as available to non-scientists as quickly and as easily as possible. And I know, again, Tom's looking at this in terms of tying it to traditional measures of agriculture impact too. Nice segue for you there, Tom, if you want to jump in.
What do you think, Tom?
Well, yeah, I mean, I can talk about static cameras. The static cameras are routinely used in the aquaculture industry. They're not normally got a machine doing the interpretation, but that can be achieved using that sort of YOLO type model that I illustrated with the Greenland sponges. So that can be in real time, or it can be uploaded and analyzed post hoc, as it were. We could certainly train machines to identify particular fish or jellyfish that are sort of going past in the water current at any point down the structure, if that was of interest. Also note here the flow cytobot work that we're doing. Again, it's aquaculture related, but it's you using holograms to identify plankton. So we can extend the image analysis from sort of megafauna to back down to microfauna, if you wanted to look at planktonic shifts in community. And we're also using eDNA in a more targeted approach to look for, I mean, again, in aquaculture, to look for sea lice, but that could easily be extended to look for particular non-native species if they were a concern to the regulatory community or anyone else.
Yes, well, it sounds broadly that it is possible to better incorporate these more autonomous, semi-autonomous sampling approaches with structures, or to streamline the analysis and so on. So a follow-on, I mean, you know, it's obviously going to take a little bit more development from everything you've all said. A follow-on question was really about costs. We've actually had a few questions today that have been about costs, and I mean, you don't get nothing for free these days. But to sort of structure this a little bit more and to help our audience consider kind of the broad cost considerations of these technologies, cost comparison studies are often quite useful here. And I'm wondering if any of our panel or Vicky working in DEFRA are aware of some useful cost comparison studies that are looking at, say, the cost of the traditional sampling and using big ships to take large crews out on site to these offshore sites versus sort of thinking about smaller, more nimble craft that can deploy and recover equipment. These sorts of studies, I think, could be quite useful for our audience to understand some of the cost implications. Has any of our panel carried out any of that sort of work, or be aware of any of that sort of work they could signpost us to?
So Henk, no, we don't have that work in train, but I think more broadly an ambition has to be for DEFRA is around how we can have how we're using technology to be able to deploy once but use many, for it to have kind of like multiple functions so that it can drive down the monitoring costs. I think that's traditionally been quite a barrier to invest in monitoring, is the large associated costs and how slow it is then to be able to return the data and translate it. So I think this is something that we're definitely looking at within the Marine NCA program, and it's about how can we work with industry to trial technology, but then work with our arm's length bodies and beyond to be able to then use it and trial it at scale. So that's something that we're definitely going to be focusing on should, fingers crossed, the Marine NCA program get further funding in SR25. That's spending review 25.
That sounds great, Vicky, and I hope so. Yes. Would you like to comment on that as well, Dan?
Oh, yeah, sorry, Tom had his hand up, but I'll jump in anyway briefly.
Sorry, Tom.
We've been trying to quantify the costs associated with our autonomous mission as part of the project. We haven't finished that yet, but we've got a reasonable idea of what it is. I think because we carried out the mission from shore, so we didn't have the costs associated with the vessel, it's going to be fairly clearly a lot less than vessel-based operations, where even the mobilization costs would probably be sort of broadly similar to the total cost of our autonomous operation. But yeah, it would be interesting. At least we'll be able to provide a data point on a more innovative autonomous solution to then compare to other people can compare to what their known costs are for more standard operations.
Thanks, Dan. Over to Tom.
Yeah, so the main cost in underwater image analysis, or any sort of image analysis, really is the annotation. So whilst the goal obviously is not to include a human in the analysis, or not to require a human in the analysis for all the footage. A human is required to do the initial annotation, to make those identifications. And that cost is as large as it is to get them to do the analysis. I mean, the benefit of the machine is that then that trained machine can go on and do an sort of infinite amount of footage if it's been appropriately trained. And the community is building databases of annotated imagery, which can be utilized by anyone that's competent to train a machine. And that machine will become increasingly nuanced and able to make the more subtle distinctions between different taxa as it's trained on more and more footage, and it'll be able to generalize more and more again as it's trained on footage. So it'll be able to generalize and make accurate predictions of taxa even in more challenging circumstances. For example, when there's shadows or where the image quality is not quite as good as it would be. It's going to revolutionize. And it really will. I mean, it already has in terrestrial environments, and it will do underwater as well. It'll revolutionize the way that we analyze or the amount of data that we get and the way that we collect the data. I think that's going to need to change so that it's optimized for a machine rather from a human's interpretation.
Yes, good answer, Tom. And just for clarity there, annotation is the process by which a human would look at the imagery on a screen, and they would using their experience identify what they're seeing in that image and label it in some way that then a machine can go, well, that arrangement of pixels is a this or a that. Is that right?
Yeah, that's right. I mean, a person's involved in the classification of images, so that's where a person says, well, this image does contain these sorts of organisms, and that's the extent of it. That's quite a rapid way of training a machine. Or you can draw bounding boxes around the training imagery, so that the machine is then able to sort of say more than, yes, there is one of these things in the image, but actually count the number of them. And that's what the YOLO model that I illustrated did. Or you can train on segmentation, which is when you draw a line around the thing that you've identified as the human annotator, and that enables the machine then to predict pixel by pixel what another image contains, and that's what enables us to generate the volume or to use a machine to inform our 3D models, because a machine's been trained to basically at a pixel by pixel level, and that takes more time. So I mean, it's horses for courses, really, and the more data that you have, and on that gradient between image classification right through to segmentation, you get more and more data out of, or more and more information out of your trained machine.
Thanks, Tom. And quickly on to Dan, and then Natalie, if she's got a comment on the eDNA costs.
I wasn't going to comment on the eDNA costs. I was going to more generally comment on the sort of the future of marine environmental monitoring. I think we've sort of seen that through the presentations, is that many of the tools and techniques we're using are starting to use remote sensing approaches rather than physical sampling. And once we get to remote sensing, we're talking about digital data sets, and then you get the potential for autonomous analysis as well as the autonomous acquisition. So I think there's really big potential in sort of making that transition and really understanding what you can and can't do with remote sensing, because there are trade-offs, and it's not the solution to everything, but it does mean that you can get data more quickly and analyze it more quickly.
Yes. So it's good to raise the concept of trade-offs, Dan, because I think there are across all decisions, really, whether you implement these things or not. And so just to finally wrap up this question, I think it'd be good to just hear a little bit about sort of any sort of cost comparison studies that Natalie or Tom might be aware of, like in the eDNA space. I'm aware costs are coming down a little bit, but do you know anything in that space, Natalie?
No, not anything in terms of comparison, but that's partly down to what question you're asking and what level of detail you want to go to. So you could effectively have bronze, silver, or gold in terms of wanting to know who's there, what their abundance is, all the way up to what are they actually doing. And costs are coming down. We do have our own sequencing facilities in-house, but we actually find it cheaper to send them elsewhere now. And there are a number of companies that do this commercially. I don't know how great they are. We're actually doing something at the moment as a comparison with our technique versus theirs, so that will be an interesting comparison itself. Interesting.
Stay tuned. Yeah. Okay.
Can I comment on that? Just
just very quickly, Tom.
Yeah, I mean, one of the main drivers for the METVAR program within the aquaculture sector was to drive costs down. Of course, the more samples you're processing, the more, you know, there are, it is cheaper to do more samples per sample. And the costs of a macrobenthic taxonomic expert that's necessary to derive the traditional metrics is just going up and up because they keep retiring and they're not being replaced, unfortunately, within our sector at the moment. So I think that differential is only going to increase where the alternative technologies are not only as accurate, but they are cheaper. And very importantly, they are much more rapid. So you get an answer within a couple of weeks with an eDNA sample, whereas your macrobenthic analysis is taken up to 6 months.
Yeah, that's, you know, that's all great, Tom. And I think, you know, I think that's going to be a kind of information that's going to help Vicky's team in the future work that they were planning there, you know, about looking at, you know, costs and benefits of these different approaches. So we're drawing the webinar to a close. I think just before we get into our final kind of closing words, it's good to see the image, the illustration that's been developing over the course of the webinar. Thank you there. It's looking really great. It's all, I can see little bits of all the different technologies that everyone's been talking about. So it's really good to see that. Thank you for bringing that up. And that'll be made available via our website. And just in the interest of time, you know, I'd like to close things down. I'd like to say a big thanks to our panel today for their talks and their discussions as well. And also big thanks to the attendees for their time and their interest in the webinar and for the topic. This is the final webinar in our series of 6 that we've run over the course of this year. And in case you missed any of the previous ones on marine biodiversity, environmental restoration and net gain, offshore wind, cumulative effects assessment, and commercial fisheries, in case you missed any of those, you can watch the recordings or listen to any of the content via podcasts. And that'll be via a link that I've just popped on your screens there. This is the Insight Impact webpage. Some of you may be interested in a written summary, in which case check out our set of policy briefs, which are produced from the content that is within each of the webinars. If you like any of this, that we've done so far, or if you've got any other comments on the webinar series, we'd be very grateful for your feedback. So for those of you who are quick with your phones and know what you're doing, there's a QR code on the screen there, and that will take you to roughly 15-20 minute feedback form that will ask you questions around the various sort of webinar products and outputs that we've made over the course of the year. We'll also send a link to this out after the webinar for you to fill out to all the attendees. We really want to better understand the impact of this research, and you all are better placed to tell us than us. So we appreciate that feedback. Just a big thanks to everyone again. And tomorrow is the 1st of December. So I wish you a great holiday season to come and hope to see you all again in the new year. So all the best and thanks again. Goodbye.
Thank you. Goodbye.
Bye, everyone.
Bye.